Hi guys, and welcome back. We are super excited about an awesome lesson today, and without further ado, we're going to go straight to Tracy.
Thanks, Indiana. Well, as Indiana said before the break, we're going to look at chemical bonding. Now, this is a really important section, grade 10, so you've really got to sit up, pay attention, and try and get the concepts. Now, remember that chemical bonding is the instance of what we're talking about in chemistry, because we look at chemical reactions, we look at chemical properties, and where all that goes. Now, up till this point, you've learned about trends on the periodic table, you've learned about how we classify matter from a macroscopic, microscopic point of view. Now we're going to get to the nitty-gritty of what chemistry really, really is about. And today we're going to look at 3 types of bonding: covalent, ionic, and metallic. Now, it's the first time in your science career that you've heard these words, and these are new, so you've got to pay attention. Now, what I've got is a very simplified diagram, because you see this sort of diagram often in textbooks, and what we've got here is we've got the white circles represent the electron clouds, and then we've got our positive nucleus in the middle, which is where our protons would be. And then what happens here, remember, is we have a second one. Now, when we talk about bonding, here, this is a very simple bond. This only represents 2 atoms bonding together. Now, the reason why I've specifically wanted you to see that we have this overlap, okay, over here in the middle, is because that is actually a very important part of the bond, because that overlap results in a sharing of electrons, and those sharing of electrons is the whole point of the bond. Remember, when we looked at orbitals, we said that they had to come in pairs. Now, atoms bond with each other because they want to fill their orbitals, and they will either do that by sharing electrons, giving electrons away, or taking electrons, but they want those orbitals to be filled. When those orbitals are filled, they get to a lower energy state. So the only reason 2 atoms will bond is they want to get to a lower energy state. Now, what I tell my learners is I tell them atoms are like teenagers. Okay, they like to be at the lowest possible energy state. So it's like when you come home from school, the last thing you want to do is work. You want to go sit on the couch and watch TV, because that's a low energy state and that makes you happy. Then bonding gives them a low energy state, okay? So let's go straight to covalent bonding. Now, we've got a couple of representations. Unfortunately, you can't see my orbitals too well here, so let me just draw these in for you. Okay, so what's happened here, it's close enough. Okay, now, here we got a little bit of a shared one in the middle. This diagram here you guys would have seen before, the one with the chlorine. I'm hoping last year when you did molecules and bonding and stuff, a little bit of bonding, chemical formulas, you did dot molecule diagrams. Okay, I'm hoping those are bringing some bells. And you would have seen this often, where it looks almost like and that's for chlorine, that they've squished onto each other, okay? And what has actually happened there, and I'm going to try to show you with my hands, is the orbitals, the outside orbitals, have come together and they have to overlap, okay? So they have to do this with each other, but if they don't overlap, we can't make a bond. And that's what we're showing there, is that they don't come together and sit together like 2 balloons, okay, or like my hands putting together like this. They actually have to overlap before the bond can be made. All right, that's very, very important. Now, with a covalent bond, it's the first bond we're going to look at. It only happens between a non-metal atom and a non-metal atom. You cannot get it with any other. It's characterized by this. Ooh, that's close, we'll put that there. It's characterized by the sharing of electrons, okay? That electron pair that's shared is very, very, very important. Now, remember, you've also learned about your diatomic gases before, like hydrogen, chlorine, nitrogen, oxygen, fluorine, bromine, iodine, and you all know they're diatomic, they come in pairs. Now, they come in pairs because when they bond together, we get a shared pair of electrons between them. Or with nitrogen, for example, we have 3 shared pairs. Very, very, very important. Now, another way for us to know whether a bond is covalent, where there will be this sharing of electrons, is to look at the electronegativities of the atoms involved. Now, last week we spoke a little bit about electronegativity, and on your periodic table, whenever you get one, the electronegativities are given, so make sure you read the key. When you take the 2 electronegativities of the atoms involved and you minus them from each other, you will get a value. If that value is less than 1.7, okay, it gives me covalent bonding. It's just a general rule. If that difference is 0, it gives us what we call non-polar covalent bonding. So that's a new word for you, okay? We get non-polar covalent bonding. Now, non-polar is actually quite important because what non-polar means for us is that we have complete equal sharing. So both atoms see the electrons for the same amount of time. So both atoms are sort of duped, if I can use that word, into thinking that they have the electrons all the time, okay? If there is an electronegativity difference, then there's not equal sharing, and we get what is known as polar covalent bonding, okay? Water does this. Water is a very important example of this. Water is a polar covalent bond. Oxygen is more electronegative than hydrogen. Oxygen has electronegativity of 3.5. Hydrogen's electronegativity is only 2.1. The difference is 1.4. It is very, very polar, okay? Which means that there's very unequal sharing, and the poor little hydrogen often looks like he's lost his electron, okay? He doesn't manage to hold on to his electron very well at all. Shame. We feel very sorry for him a lot of the time, and a lot of time his electron just gets taken off by metals and things that are far more excited to have them. But non-polar, polar, non-polar, equal sharing, polar, non-equal sharing. But covalent bonding, whether it's either of these, means that I have a sharing of electrons, which then completes my orbitals. How do we represent it? Lewis structures is an important structure for you to get. Now, what a Lewis structure does is a Lewis structure shows me the valence electrons. Now, we spoke about valency in one of the first weeks, and we spoke about valence electrons. These only show my valence electrons, because remember, as we go down the periods, we keep adding energy levels. Now, we don't need to see the inner energy levels. They don't do anything, okay? They're not required for bonding, because they're complete. Now, if you look at your group 1 elements, and this is why hydrogen's in group 1, there's only one valence electron. So there's only one electron drawn. This is an unusual format of it because the hydrogen is drawn with your electron on the side. Generally, we'll draw it at the top. Then we get to group 2. It has 2 valence electrons. Note that we put them separate. We don't put them together, but they're on 2 separate parts. So you can think of, and it's a good way to think of it, is when you look at this, is you can go, well, there should be an electron pair, 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 okay? So we're looking at the fact that it's almost like our Aufbau diagrams where we build them up and we have the 4 orbitals. It's the same concept, but we're only putting them around the atom as we go along. Now, as we go along, we keep adding in, and this actually helps us a lot with our bonding, because if you look at nitrogen, for example, nitrogen has 3, whoops, and this moved. Anyway, let's just make sure it doesn't look again, because there we go. Now, nitrogen has 3 open spaces. Ooh, let me change color halfway. Anyway, has 3 open spaces. That means it can make 3 bonds. This is what makes nitrogen so special. Carbon and the group 4 elements, the fact that carbon can make 4 bonds is why carbon has a chemistry all to itself known as organic chemistry, which you're going to get to in grade 11, and I like that section. As we go along, we realize that the electrons, the outer orbitals are getting fuller and fuller and fuller, which means we need less and less bonding, and also this helps us with electronegativity. As we move across, good thing to think about in your head is, would it be easier, for example, for magnesium to gain 6 electrons in order to fill its outer shell, or to give 2 away? I'm hoping all of you are screaming at the TV right now and going to give 2 away. Of course it is. We come down to fluorine and chlorine, and we go, well, fluorine's got 7. What's easier, to give 7 electrons away or to take 1? Absolutely to take 1. That's also why fluorine's our most electronegative atom, because it only needs 1 electron, and it has a very small energy level, and it makes it very, very stable. So that's what it likes, okay? What does that mean for us? Well, if we draw our Lewis dot notations, now this is going to come up and I want to see the bonding. I've got 3 examples, and they all go from single bond to double bond to triple bond. Hydrogen only has 2 electrons, okay, because it has 1 electron in each of its outer shells. We put the shared pair of electrons in the middle. The bond must go between the 2 atoms involved. That's very, very important. When we come to oxygen, oxygen is in group 6. It can make 2 bonds. That means it can make a double bond with itself, okay? Please take very careful note of where I've put the other electrons, okay? Also, I want you to see, now some teachers do this and there's nothing wrong with it, it's just a way for you to see, but we really shouldn't put this in our diagrams, is there is my oxygen, the 1 oxygen, and we've got 8 electrons around it. Here's my second oxygen, also got 8 electrons around it, and there's our shared pairs. And if I draw a line from each of these, that shows I have a double bond. A double bond simply means I have 2 pairs of electrons being shared. Nitrogen's the same. Now, this is why nitrogen forms a triple bond. It's also why nitrogen is so inert, because this triple bond is extremely strong, okay? Is if I circle that nitrogen, it has 8 electrons. If I circle my other one, it also has 8 electrons. Happy, okay? Plus, I can see that I have 1, 2, 3 shared pairs. So the nitrogen is very happy because it has 3 shared pairs, but it's got C's 8 electrons. Happy as a pig in mud, as the saying goes, okay? But this is all well and good because these are our diatomic elements. What happens when we look at ones that aren't diatomic? Okay, so now I've got some extra examples for you, and these are ones that you're going to see quite often. They're very, very popular. Grade 10s, also in some of your books, you will notice that they use dots and crosses. The crosses are there so that you can differentiate between the 2 atoms and which electrons come from which. But please remember, because sometimes that leads to the misconception that the electrons are different. No, they're not. Whether the electron comes from hydrogen or chlorine, it's still an electron, okay? And in fact, Lewis, when he did the system, only used dots, okay? The crosses are just there as a guide to help you. All right, so if we look at hydrogen and chlorine, hydrogen gives 1 of these little electrons, chlorine gives the other 7, okay? And here is my shared pair, single bond, very happy. Water, now we've got to say, well, how do we know where the hydrogen must go? Because that's a very common question. If we go back a step and we go, well, oxygen has this Lewis structure. Okay, so we've got its 6 little electrons, and the 2 open spaces are right next to each other. These open spaces are exactly where the hydrogen is going to want to bond. It's not going to want to go anywhere else because hydrogen only has 1 atom. So that's how I know that then I would put my hydrogen over here, and I would put my other hydrogen over there, and that gives water its nice angular shape. Okay, and I sometimes teach my kids, it looks a little bit like Mickey Mouse ears. Okay, so if you draw it as a dot molecule, I'm hoping you've seen this, you probably would have been told, we often draw it so it looks like that. Okay, with the oxygen in the middle, 2 hydrogens on the side, and we know it's going to look like that because of its dot molecule, because of the Lewis structure. Okay, hope you hanging in there. And then ammonia, very, very, very important molecule as well. Nitrogen has 3 empty spaces, so nitrogen can take 3 hydrogens in each of these, and it goes and it fills all the empty spaces. This pair of electrons here at the top has a very special name. They are called a lone pair. Okay, now a lone pair is just that. It's a pair that stands alone. They're not bonded to anything. Oxygen has 2 lone pairs. Hydrochloric acid has 3 lone pairs. Now those lone pairs are actually quite important when we look at intermolecular forces and stuff a little bit later on, so we're not going to spend too much time on that. Alright, so basically what you need to get from covalent bonding is that it's a sharing of electrons between nonmetals. Getting on to our ionic bonding. Now ionic bonding is so important. Sodium chloride, you see this all the time. It is very, very special. It's the bonding between a metal and a non-metal. Now, what happens in ionic bonding is the electronegativity difference between the atoms involved is so big that the chlorine or the non-metal will take the electron away from the metal. I usually, to help my learners remember it, I usually tell them the metals are like really bad parents. Okay, they're not really concerned about the electrons. In fact, they're like, okay, if I've got it, I got it. If I don't, oh well. Okay, but chlorine wants them desperately. Okay, now what we've got is, this picture, the one on the side didn't come out as well as I would have liked, but this shows this middle picture shows such a nice structure of what your ionic bond does. It creates a crystal lattice. And your ionic solids are generally quite hard, they brittle, they break, they shatter. Your covalent solids are quite malleable. They're not as hard, they're not as, they don't shatter, they're not brittle. It's like candle wax is a very good covalent solid, okay? Now, we've got to add in a couple of extra words that come here because a metal gives away its electron, okay? So it becomes a positive ion. Now, that makes it a cation. Okay? Now, I remember that the cation is positive because I quite like cats. So it's a cation, so I quite like it, and that's a positive thing. Okay, so that's your metal. Your non-metal gains an electron and becomes an anion. And now, anion looks a little, and it's bad spelling, but it looks a little bit like the word onion. And onions make you cry because they're negative. Okay, so your cations are positive, your anions are negative. Your non-metals always become negative. There are no exceptions to this. And when these bond together, we don't talk about, so when I say that I've got sodium chloride, this is what we call a formula unit. Okay, it's not the same as a compound because only covalent molecules are considered to be compounds because of their bond. This is a formula unit simply because it is practically impossible to separate a single sodium ion and a single chlorine ion in sodium chloride. You cannot get a single one of these. It's virtually impossible. However, with your covalently bonded substances like water, ammonia, it is possible to get a single molecule. But it's difficult, but you can do it. You can't do it with your crystal lattices because now these are held together. They're so strong because we've got positive ions, negative ions, and the electrostatic forces, which you learned about in grade 9, are very, very strong. So they have a positive charge bonded to a negative charge. They're very attracted to each other and it holds very, very tight. Okay, it's also why sodium chloride has, or any of your ionic solids have a high melting point, high boiling point. They're always pretty much solids. You don't get them in gas form. Okay, in terms of how we show this with Lewis structures, now we've got to show the difference in the fact that we're not sharing electrons, we're actually transferring electrons. And we show this by going, well, sodium has a single little electron, which it's going to give to the chlorine. Okay, and what happens is we get a sodium ion and we get a chlorine ion. Okay, and when we write it in this way, I show the positive and I show the negative, and that helps me get to the fact that the formula is NaCl. Okay, if we were looking at, let's use magnesium. I just want to show you one more example. Okay, so magnesium, which is in group 2, okay, if we add it to chlorine, and we have chlorine, which is in group 7, and we go, well, my magnesium is going to give its electron away. Can you guys see that there's a problem here? Because magnesium still has another electron, but chlorine's taken it, which means I actually need to have another chlorine here. Okay? And what's going to happen now is my magnesium's going to get very happy because it's going to give its electron away. How do we represent this now? Because we don't want to have to keep drawing everything. So when we draw it here, we go, well, magnesium has become Mg2+, because it lost two of its electrons. And what we have is 2 chlorine ion, negative ions. We have 2 of them. But do we ever write a chemical formula with the number 2 in the middle? Of course not. That's the little 2 that becomes our subscript, which means we would then write this as MgCl2. Okay? Now, you've learned a whole bunch of rules on how to do formulae, but this is also one way to work it out for yourselves. Okay? Now, our last bonding. Okay? Our last bonding. Metallic bonding is very special. Metals, we call it metallic bonding, but it's a little bit misleading because metals don't really bond with each other, okay? Because they just don't. They form what we call alloys. They form metal mixtures. By metallic bonding, what we're referring to here is what keeps metals as metals. Why do they stay together? And their bonding actually explains why they're good conductors of heat, why they're good electrical conductors, why they're malleable, why they're ductile. It's because of their bonding. Now, most of our metals have got quite a few number of energy levels. So their outer electrons are quite far away from the nucleus. So you know what? It's a little like that old nursery rhyme about the woman who lived in the shoe and had so many children she didn't know what to do. It's the same thing. These poor little atoms have no clue what to do with themselves because now we've got all these electrons and these little nucleuses are like the parents going, I can't keep track. So what actually happens is we form, the nucleuses stay put. They sort of go, this is my house and I'm staying here. And as long as they can see enough electrons, they don't care where they come from. So what it means is the outer energy level of our metal has pretty much, they all just sort of mush into one. Okay, it's a bad way to describe it, but I'm hoping it actually helps you understand it. And my metal bonding has gone for a little bit of has decided to go running around the TV. But anyway, so we have these electrons here that are very happy to move around. So they go from house to house and jump along, and they're very, very happy. So what that means, okay, let me just do this so that it can actually stay in place. All right, is these electrons here can just move, and they move along, and when we put an electric current through it, that means the electrons are forced to move in a specific direction at a specific time. That gives us our current. At any other time, they're pretty much moving randomly. But you've got to get this. The nucleuses, the nuclei, better word, are stuck in place. It is often described as a positive kernel. Okay? It's a positive kernel. That means it's a positive set, okay? It's a positive kernel, and that's the nucleus, plus the first couple of energy levels, okay? And then we have, and now this is quite an important word. I just want to do something quickly just to distract, to get rid of something quickly. We don't want that, there we go. Okay, now, these electrons, these electrons, very important word, are known as delocalized electrons. Okay, delocalized electrons. They do not have a home. They can go anywhere. When we make an alloy or a mixture of metals, the positive kernels stay, electrons can move through. So it's not the same, it's not sharing, and it's not transfer. Okay, it's sort of like a smushing of the electrons together. If we look at, and we're going to look at something simple, let's look at HF. Maybe I should have a thingy for you. Okay, hydrogen fluoride. All right, now, hydrogen fluoride is a strange little creature, okay? Because we have our hydrogen, and we have our fluorine, and fluorine sits in group 7. And now, if you go to your electronegativities, and remember I said to you, it's got to have electronegativity difference of less than 1.7. Fluorine's electronegativity is 4. Hydrogen's electronegativity is 2.1. So they have a difference of 1.9. That is huge. But this is not ionic. The reason why I know it's not ionic, it's two nonmetals. So it's a little bit of an exception, which also means that the hydrogen doesn't lose its electrons, doesn't become negatively charged, okay, and the fluorine doesn't actually gain, it shares it. But this molecule is what we consider to be very, very, very polar. Remember I said to you that means positive and unequal sharing. Fluorine pretty much looks like it gets the electrons not pretty much all the time. So that's what happens with the fluorine. Actually, hydrogen fluoride is what we call a corrosive acid. It doesn't have a very high pH like HCl, but you cannot store hydrogen fluoride in glass bottles. It eats through glass. So none of your schools will have it, and it's extremely, extremely dangerous. What about, I now say to you, I want silicon oxide. Okay, so I'm telling you, I want to know what the formula is going to be with silicon and oxygen. I'm not going to tell you whether it's got 2 oxygens, 4 oxygens, what the case may be, but silicon is in group 4, okay, and I know that for sure because it's underneath carbon. So silicon, oh, I've lost my yellow, that's gone on holiday. There's silicon's bond, looks like carbons, okay. Oxygen looks like this. Now, here is where things get interesting because silicon isn't a metal or a non-metal. It doesn't really know what it is. It's one of those metalloid things. So we're going to consider this to be a covalent bond, but now I want you to see something. One electron can go here, and one electron can go there. Do you realize that we have a problem? That there actually isn't enough electrons for the silicon, which means I need another oxygen. Because now the silicon can make the bonds it needs, so it does this. Oops, sorry. And it's going to go here. And in fact, I'm hoping you all recognize that this looks exactly, when I do it nicely, carbon dioxide. Okay, looks just like carbon dioxide, all right? Which is actually quite cool.